back, everybody. Let me just take a quick in-class attendance. You don't need avatar. Just a small class, everybody know each other. Don't worry about it. Okay. All right, good. Oh, that's it. All right. So Thursday we have exam. Do you have any question about exam? Let's just take care of it before we move into Unit C. Go ahead. Yeah, either one's fine.
Okay, so to prepare for it, should we just go over all of the problems and the notes and the homework and just make sure we can do them?
That's a good idea, yes. I wouldn't go against it. Make sure you go over the notes and then understand the concept, and then make sure all the examples we did in class covered up. In other words, I want to see your notes at least complete form, no white spot. That's usually what the problem comes from. You know the rule. If I skipped this example problem in class, that actually showed up in major exam. That happens all the time. So make sure you don't do that. And then obviously homework assignments coming almost straight from those example problems. Okay. And then quizzes, of course, quiz is a little bit more challenging because I force you to go back to aerodynamics contents. You need to kind of review it and then go back to aerodynamics notes and then refresh your memory or run from scratch like Jordan. If you have to do that, not too bad, but you have to do it. So those are very healthy way to prepare for the exam. Okay. Now, one big hint for you. I don't want to record it, but yeah, it's too bad. I started recording, so anyways, record it. I'm going to let you read off NACA chart, guaranteed. You have to read off the data. So make sure you don't make a mistake, such as read off the CM quarter code value using CL scale. That's a typical mistake. You don't do that. So program will involve reading off the NACA data from the chart, which we covered heavily in aerodynamics. So most of you are okay, except Jordan. Again, I guess Jordan, you can of course pick it up. Don't worry about it. Okay, but it's a big hint. NACA, maybe standard 4-digit chart. You know how to pick up the data from that chart. Okay. There are a few example problems we did in class, and also some of the homework assignments requires those read off. Yeah. Okay. Any question? Yeah, go ahead.
I know B3 is due after the exam. Is that also possible to be on the exam?
Unit B3 is kind of interesting unit because in Unit B3, what it is, it's a special subject which covers like a high-speed leading edge design, like a supersonic leading edge versus subsonic leading edge kind of thing, depending on the Mach angle, and also pitch up tendency. Plus, we talked about scales, right? Then we walked through like the pictures and all that. And then the rest of the Unit B3 is essentially example for project phase 2. This is F-16 whole aircraft analysis, which is basically example coming from Unit B2. Let me just take a look at Unit B2, okay? So if you look at the Unit B2, okay. So Unit B2 actually consists of a fairly humongous amount of equation after equations and make you feel very confusing. In other words, starting from here, whole aircraft calculations. This is actually, hand calculation method to predict your lift and then your drag of your entire airplane. Plus, if your airplane goes supersonic, you have to add a wave drag component. How can you predict it? And also, what is the critical Mach number, drag divergence kind of thing. So this is the hand calculation, very classic Air Force Academy style, coming straight from Dr. Jeff Ashworth's 100% entirely hand calculation-based prediction method for airplane lift and drag and high-speed drag. Okay, so this equation is going to be actually put into practice in Unit B3. Okay, so that's the context of this thing. Okay, so this is the whole aircraft analysis. This is example. basically picking up all the equations introduced in Unit B2 and then actually doing it here. Okay, so Unit B2 notes and Unit B3 example come side by side. And then that is something you have to do in project phase 2. And then, do you think I'm going to pick up this kind of problem for exam? That is essentially, I'm motivated to flunk everybody. That's what it is. If I do, such a thing. So you can probably 90% ish, you can assume, oh no, Dr. H is not going to do this. He's not evil. Although 10% chance I can freely pick up some of those things, cut and paste and make it into exam. That's a nightmare exam. If so, I don't think it happens. But this is something you have to do in phase 2. Of course, at least one team member who don't show up in class, you have to do it. You have to sacrifice that team member to do all of those hand calculations. You don't have to actually use your hand to do this calculation. You can pick up your software, of course, right? It's just not X-Prior 5. That's what it is. It could be MATLAB, could be spreadsheet, could be some other software. That's fine. MATLAB, like, I don't know, symbolic math toolbox with drive editor or something. If you are cutting edge and sharp on MATLAB field, you can do that. Okay. Anyways, I hope I answered your question. Is that correct?
Yeah.
Okay, good. Any other thing? Do you have any specific question problem you are struggling with or something like that? I can take care of it today. If you're happy, I'm going to move on to Unit C, performance. Those aerodynamics is over. And if you want to keep going on and on, trying to sabotage, you can do that. Either way. People online, you can do that too. Yeah, go ahead.
Are you going to have anything where we're deriving like aerodynamic concepts?
Am I going to make you derive the equation? Is that your question?
Sure.
If you see such a homework, I may cut and paste and let you do it anyway. But if you don't see any homework that actually involves equation derivation, do you think I'm the guy all of a sudden I let you derive this equation in exam? I don't think so. Go ahead.
Are you going to give us a formula sheet?
Formula sheet is going to be integrated within the program statement.
Okay.
Yeah.
Right. So then we don't need to memorize any of the or learn any of the.
Yeah. Again, memorization. Let's just. I don't want to even use that word. Memorizing is like, okay, do I have to memorize this formula? That's usually. I mean, I expect you to know those things, but you don't have to memorize. That's my answer. So it's like. It's like, of course, you have to pick up some equations, plug and check if you need to do that. But you know which equation is the right equation. You know what is the constraint. You know what is the origin. If you need to derive, I can kind of thing. That's what I expect. Okay. It's totally different from memorization. Yeah, so you are not in that level. You know aerodynamics. You know airplanes. That's what I expect. So you way past that stage, as you go through aerodynamics. Okay. Aerodynamics students are going through that stage, though they always ask me a dumb questions. I say, oh, do I have to memorize this formula? This is so complicated. Wait a minute. Look at this homework. This homework asks you to derive this thing. Did you do this? Did you do this? Did you do this? Did you understand the process? Well, I worked together with my friend, and the friend showed me everything. So do I have to memorize it? Well, if that's the only thing you can do, go ahead and memorize it. I mean, that's not engineering at all. So, sorry, I oftentimes get kind of upset in the middle of the lecture. I say those bad things. I don't want to. I don't want to say that to you. Exams should be super easy. Okay. If you're doing whatever you are supposed to be doing. In other words, number one, show up in class, of course. People who are watching this video, I have to tell you, you have to show up in live session. You have to ask questions, very good questions. Even dumb questions, fine. I mean, you have to show up online. Not online. In what I'm talking about. Live. It doesn't matter online or in class, but the live class. You have to stay alive, asking questions, try to understand the concept, try to communicate. Number two, take a very good notes. Okay, the notes containing every information I need. No information missing from that notes. As I cover the example problems, you understand completely. You went through it by yourself. You even punched the number with your calculator. This is not calculator, but you punched the number and then confirm this is correct. And then you apply to that homework and then quiz. And then it's okay to still make a mistake, but you corrected everything. If you did that, exam is not exam, it's entertainment, like I said. You laugh at it and finish up and make a joke about it. And then walk out of the classroom and then you get, oh my goodness, 97, what did I do? There's always some stupid mistake in it anyways. So that's ideal engineering student life. Okay? So that's something you've been chatting, right? David and Jimmy's. Like, oh, you know that class, blah, blah, blah. I didn't listen, but that's your ideal engineering life. So I hope that happens on Thursday. Okay? Don't worry about it. But if you're not doing any of those, you have to worry about it like hell. Of course. Well, that's where exam anxiety comes in. Because AE students always say, oh, I have a terrible exam anxiety. That's why I did bad. Yeah, right. That's my response. Yeah, right. Okay. So are you ready to step in to performance? Okay, so now aerodynamics section is over. So now we are going to take a look at as a whole airplane in flight. So how can we compute and predict the performance of airplane? Performance of airplane, you require information of aerodynamics. So that means you need to design airplane, and airplane comes in with certain aerodynamics baseline data, such as how much lift you can generate, how much drag you're going to have. In other words, this is the drag this airplane has. That's the drag Porter plot. At the stage of phase 2 of the project, you're using XFlyFi to come up with, as a whole airplane, you need to have a drag Porter plot. This kind of plot. Let me show you that. So as you look at, drag Porter plot, you don't have it. So it's probably unit B2. Let's take a look at unit B2. Drag Porter, okay. So the very first thing you need to come up with in Unit B2 is this kind of plot. Here we go. So this is a whole airplane drag Porter, this thing. Okay? So as you design and build your airplane, the entire airplane comes up with a drag Porter plot. This is the plot of lift coefficient against drag coefficient, drag Porter. This drag Porter is going to be expressed usually using polynomial function second order. It could be completely symmetrical, or it could be shifted to the right side. It depends on everything that how you design and configure your airplane. So some of the airplane shows that minimum drag point, okay, is shifted. It's not going to happen at the CL equal to 0. In other words, you know CD0, okay? CD0, what's the name of CD0? What is this thing? The name is what? Zero lift drag coefficient, right? Or parasite drag coefficient. So that means if airplane is not producing any lift, how much drag do you have? That's called CD0. This is typically the minimum point, right? So this is CD0. But depending on your configuration, your airplane may come up with a CD0 right here. This is CD0 still, but this is not the minimum point, right, of a drag. Minimum point shows up right here. It's shifted. Why this happens? This is actually something called camber effect. This is as if your entire airplane configuration comes up with a cambered wing. So there's a shift. So in that case, you would rather interested in what is the value of CL minimum drag, CL min D. Because this is what the drag coefficient is lowest. So you need to keep track of it, okay? Not the CD0, right? And then this CL minimum D affects on certain type of performance of your airplane, so you have to know. So this kind of data is like a final sets of data you really, really need from X-5. This is the starting point of your performance analysis. So this is your airplane's characteristics in terms of aerodynamics, how much drag is associated with how much lift, or how much lift is associated with how much increase of drag. Where is the minimum point of the drag? Because that's the point which is quite important in order to maximize your range endurance, other things. Where is the exact location you need to keep flying? If you maintain that condition, you can possibly optimize your range, optimize your endurance. By the way, endurance and range are different. I'm always confused with it. Okay, that's one of the reasons why I didn't understand the flight mechanics when I took this class when I was an undergraduate student. So funny thing is, I didn't quite understand flight mechanics when I took this class. I hated to death. That's why I ended up being aerodynamics. So this actually doesn't belong to aerodynamics field. This is like airplane designer, flight mechanics, and performance. It's not really aerodynamics. It's based on aerodynamics, but it's not, okay? So again, I did my best, and as I create my notes, and then also original textbook of Air Force Academy included so many mistakes. I had to correct it, and that actually made me train up to understand better a little bit. So this semester, let me try my best. So let's just move on, starting from here. This is the starting point. Whole airplane drag polar. Do you know the name of this? This is a starting point. This is called something called TR. What's that? So that's required. Okay? This is the starting point. So your airplane, as you design your aerodynamics, and then you come up with a configuration, you're going to determine thrust required. So this is going to be a driving factor of what type of engine you need to choose. Of course, you have to have a bigger than this thrust required type of engine, otherwise your performance is so poor. Sometimes your airplane cannot even fly. And then if you choose the bigger and heavier engine, that is actually going to affect back into your airplane. That means the airplane is too heavy. You have to beef up your structure and becoming more heavier, and then changing your CG point. Oh my goodness, this is not stable anymore. Okay, so that's all about trade-off, right? So your software X-5 takes care of mainly the aerodynamics component. Plus, that software is also capable of taking care of like how heavy your airplane is. You can actually determine the mass point, determine the location of the engine, and then you can put the engine's thrust power and stuff like that. You can change flight configuration, flight conditions, other things, and then you come up with a different thrust required plot that is going to reflect it back into the performance calculation. So there are lots of iterations. So even if I say hand calculation, don't literally use the paper and pen and hand. It's a bad idea. So please come up with some kind of software, okay? All right. So let's begin with Unit C, performance. Okay, so starting point is aerodynamic design, which is essentially you're going to come up with the entire airplane, whole airplane drag polar. That's thrust required. Okay, so let's just take a look at Unit C1. Unit C1, I'm going to begin with the very fundamental idea, equation of motion. Now, equation motion, here we go back into all days of dynamics. I don't know who the teacher was, but the dynamics class was so much fun. This is essentially single body dynamics. Airplane treated as a single body dynamics. If it flies straight, of course, lift equal to weight, thrust equal to drag. That's a straight level unaccelerated flight. So that is essentially single body dynamics, right? Straight motion. If airplane turns, it is a turning motion, right? You have done that, right? Centripetal acceleration comes up. You're going to balance against leaning toward that. That's a bicycle. So it's fairly similar to dynamics class. So be ready for it. Equation motion. This is essentially dynamics. And then today, I think I'm going to spend some time talking about aircraft propulsion systems. Of course, you have a tremendous range of selection of a propulsion system. You can choose to go with electrical motor, with a prop. Depending on the size of airplane, you can choose to go for like a different type of turbojet, turbofan, type of prop type of engine. You can choose, of course, the regular piston engine propeller type of configuration. You can do lots of things. And then there's a slight difference in computation between different type of propulsion system. You shouldn't miss that kind of detail here. Okay, you can choose any type of propulsion, then you can integrate within your software X5 to a certain extent. Okay. All right. So first of all, equation of motion, page 2. This is essentially classic dynamics, single body. So there are a few important things that if you make this kind of mistake, it is going to make a Professor Ken Bordignum very upset. One thing he gets very upset is, oh, you know, today I couldn't believe that the students couldn't differentiate between angle of attack and the flight path angle. They think those are the same. Damn it, he exploded. So don't make that kind of mistake, okay? And come to think about back in, like, I don't know, 5 years ago, I probably didn't know the difference because I'm aero guy. I was not flight mechanics guy. Anyways, so let's just to take care of those things, okay? So first of all, angle of attack, alpha, of course, you know that. This is basically the angle between aircraft reference line, usually the code, if it's a cross-section of a wing. If it's a main wing, it's a code. If it's the entire airplane, it's usually nose to tail. Nose to tail line, aircraft reference line, some kind of reference line having an angle against relative wind. It's called angle of attack alpha. Okay. Now let's define flight path angle. Flight path angle, this is gamma. This is called flight path. Flight path is essentially the angle between horizon to the direction of relative wind. That's called flight path. Okay, that's what your airplane needs to take the flight, measured relative to the horizon, because your airplane comes up with the direction of velocity. In other words, that the direction of the velocity may not necessarily be lined up against the relative wind. So this is t, this is the direction of the velocity of motion. So this is where the direction your airplane is moving toward, okay? Oftentimes, this direction have an angle against relative wind. This is called alpha t. This is called thrust angle, okay? So lots of things here. So gamma is a flight path angle, alpha is angle of attack. Alpha t is the thrust angle, okay? Now those are all different, potentially be all different values. Alpha, gamma, and alpha t, okay? All right, now typically the direction of the velocity is usually lined up completely against relative wind. So there would be a typical situation that alpha t becomes 0. That's okay, oftentimes alpha t is very small and then could be 0. Alpha t, yeah, here we go. Okay, so for many airplanes, it is acceptable to assume that the thrust vector is approximately aligned with the velocity vector. If you put alpha t equal to 0, you can simplify this equation a little bit. In other words, cosine 0 is 1. So thrust is the thrust in the direction completely against relative wind. Okay, and also the other assumption is if your airplane is completely flying toward the horizon, that means flight path angle is 0. Okay. Flight path angle is 0. This is sometimes called straight level unaccelerated flight, SRAF. Straight level unaccelerated flight, SRAF. This is going to further simplify those two equations into very simple format. Thrust equal to drag, lift equal to weight. This is condition of straight level unaccelerated flight, SRAF. So we are going to start with SRAF to begin with, okay? And then we are going to add acceleration toward positive y direction against gravity that is actually climbing. And then we are going to take a look at the, going to the this way, the other way around. This is the gliding. So climbing and gliding, we are going to add radar. And also we are going to add a turning. Straight level turn without losing altitude. That's a simple turn. And also vertical turn, 360 degrees. Loop turn. We are going to take a look at those things based on the equation of motion, okay? And then out of those very simple dynamic analysis, we can predict the performance. In other words, we can find out those things. Aircraft performance, okay? So you're going to predict what an aircraft can do. You design your airplane, and you want to know how much we can do, how fast you can fly, and how high it can fly, how quickly you can turn, what is the turn radius and rate of turn, those kind of things. How much payload you can carry, that's important for SA-18. You probably don't care about any others, just the payload. If I can turn, I'm okay. But if the turn radius is 1 kilometer, you can never come back to your original point. So you really need to think about those things too. But how far it can continue flying this range, right? Yeah, okay. And how short or long a runway can be or needs to be for takeoff and landing, and also how long you can stay up in the air. That's called endurance, range and endurance, takeoff and landing distance, which is constraints for your airplane, especially if it's a passenger type of airplane. This is the fastest speed, and this is the seating, and also climb rate, and then sink rate for your gliding. How can I minimize the sink rate if you're designing like a glider type of airplane? That's quite important, okay? So those are the kind of things you can compute, and then you have to make sure that your original design motivation purpose, does it meet for those things? So this is a performance computation. So it's based on the aerodynamics. So Xflyer 5 can provide you a basis of data and information, and also you can use the software to a certain extent. But most of the time, you have to come up with your hand calculation, okay? So first of all, airplane weight. Weight could be empty weight, weight of the fuel, and weight of the payload. So total airplane weight is empty fuel and then payload. And then payload could be permanent payload and expendable payload. Really, what are those differences? Expendable is like ammunition you can drop. Permanent payload, like passenger. Like, well, luggage is not permanent, but you have to add always kind of payload. Okay. Do you have like a permanent payload for your airplane? That's a hunk of rock, metal. Okay. That's right. So sometimes you want to separate those two categories. It's for your convenience. All right, next page is the propulsion. Let's take a look at propulsion today, okay? So you have a choice of propulsion system to fit into your airplane. Of course, you need to carefully look into, first of all, the sizing. Basic sizing is what is your Mach number against engine maximum thrust to weight ratio required. What is the thrust to weight ratio? Let's just take a look at it. So this is the engine maximum thrust to weight ratio is the TSL. This is sea level thrust. Maximum thrust you can get is a sea level divided by weight of the engine itself. This is called maximum thrust to weight ratio. So this is going to come into the factor. That means how strong your engine is versus how heavy your engine is. That's called maximum thrust to weight ratio, is a y-axis here. And also this is a flight Mach number. So suppose if your airplane is a subsonic airplane, and then this maximum thrust to weight ratio is fairly low, your choice is probably this one, piston engine propeller. So most of you actually ended up with piston engine propeller type of configuration, which I wouldn't surprise for that. Some of the team may choose the turboprop over it. Now, turboprops is a better choice for what kind of situation of a piston engine by looking at this thing. It is overall engine thrust to weight ratio goes higher. That is, thrust overpowers the weight of the engine for the low end of speed. It looks like that. That's the turboprop. And also, if you go supersonic, your choice is kind of limited. Now, at that point, your piston engine goes out. Well, you can't use that. Turboprop is kind of limited. But you can still go for high bypass turbofan to the certain extent to the high speed. Turbojet take over, supersonic. And then what's this? This is rocket, isn't it? Yeah, that's right. Oh no, this is ramjet. So ramjet works very good in high Mach number. So this is afterburning turbojet, but of course you have to consider the fuel consumption for that. Afterburning turbojet turbofan, those two, okay? So this is one category you can kind of pick up your propulsion system. The other one is quite important, engine thrust specific fuel consumption, TSFC. This is how much fuel you're going to consume in order to generate certain amount of thrust. Now, be careful about that. In this unit, I just keep using T as a thrust. T is a thrust, okay? So temperature, I'm going to use temp. Temp is temperature. So I just differentiate. Because it's so confusing, okay? So T, if you see T here, it's a thrust. So oftentimes TSFC is represented by CT. This is a thrust-specific fuel consumption. So this comes with a very weird unit. It's inverse of time. Usually TSFC is an inverse of hour or something like that. So oftentimes you have to convert it to seconds in the equation. But be careful, stay consistent. If the fuel consumption rate has units of pound per hour, and then thrust is in pound, of course, TSFC becomes inverse of an hour. Let's just keep track of your unit system. Let's be careful about that, because usually hour is not the standard unit. You have to convert it to second, typically, okay? So next one is an operating envelope. Let's take a look at operating envelopes, yeah? Oh, okay. So this is a TSFC plot for lots of different engines. TSFC high is like a consuming fuel. TSFC low is usually a better choice, right? So this is a rocket, always constant. Okay. So rocket, interestingly, fuel consumption is constant almost. And then ramjet does very well in high speed, not so for low speed end, it looks like. Afterburning turbofan turbojet, you know, fuel consumption goes up by sacrificing fuel consumption, you're going to get more thrust. That's what the turbofan turbojet afterburning really is. And those are like a low speed end. This is a piston engine propeller. High speed end, you have a tendency to consume more fuel. High bypass ratio turbofan is fairly flat. Low bypass ratio turbofan just increase in high speed end. Turbojet also. Turboprop really high. So in other words, turboprop is suitable for low speed. So you can say those things by looking at this TSFC plots. The other one is pride envelope. So this is a plot, okay, of to-do airspeed knots. By the way, to-do airspeed in knot is what was that? To-do airspeed. TA. KT. Knots. Okay. K. Knots in to-do airspeed. KTAS. KTAS. This is knots in to-do airspeed. How's that? This one. KTAS. Now you can have a equivalent airspeed. That means knots in equivalent airspeed. KETAS. KTAS. Well, anyways. So equivalent and then true, the difference is the density. If you use the standard sea level density, it's going to be called equivalent airspeed. True airspeed requires actual density, okay, or required conditions. So in this case, KTAS. This is an altitude. So this is the flight envelope for each different type of engine. So which engine is suitable for true airspeed range and also altitude range. So if you are designing high speed and high altitude, your choice seems to be kind of limited, either rocket or ramjet kind of thing. If you want to fly mainly low speed but high altitude, one choice could be turbofan turboprop or piston prop type of thing. So depending on your range of altitude and then through airspeed, you can pick up your propulsion system. This is called propulsion system flight envelope, operating envelopes. Okay. All right, next page. So let's just take a look at each type of propulsion system one at a time. First one is piston engine / piston propeller. Those are usually combination of those two. Okay, so the power produced by a piston engine, it depends on the size and the number of cylinders. Did I take the picture of engines? Yeah, I think so. I took some pictures from Ohio U.S. Air Force Museum. I probably want to bring it in next class. There are quite a few interesting different type of engines displayed, starting from like a very old style, like a 6-cylinder radial engine, all the way to like a 2,500 horsepower WASP, twin WASP or something like that. So it's kind of interesting. So this is a piston cylinder configuration. This is 4-stroke engine, right? I guess so. So this is like a similar to automotive type of engine. And then shaft horsepower SHP. Engine's horsepower is usually measured by connecting to the dynamo and then measuring the horsepower through that shaft. It's called shaft horsepower. Engine shaft horsepower SHP ratings is a 1 horsepower or kilowatts in standard sea level conditions at a specified maximum rotation rate. So this SL stands for sea level. So as you increase your altitude, of course, you're going to lose the shaft horsepower, obviously. So the maximum possible shaft horsepower is available at the sea level only, okay? All right. And then propeller is usually attached to it. So oftentimes you're going to combine propeller efficiency with the shaft horsepower, and then you're going to come up with the thrust available. This TA is quite important. So this is the thrust available. So your X-Flyer 5 whole airplane analysis is going to provide you thrust required information. So thrust required is going to be combined with thrust available. So you are going to have some excess thrust. So how much excess thrust do you have at each flight condition or configuration of the flight is going to be contributing to your performance, okay? So thrust available, thrust required is going to show up next, okay? So this is a different type of engine, something called turbojet with afterburner. And also, if you have a bypass here, this is called actually low bypass ratio turbofan. No, this is turbojet. There's no bypass. No, okay. So this is pure turbojet. This is turbojet with afterburner. Okay, good. So let's just take a look at the turbojet engines to begin with. Turbojet engine is basically mass flow rate times you're going to accelerate airflow inlet into the exhaust gas. You have a high-speed exhaust gas comes up. This is going to change the linear momentum of the through flow. This is going to contribute to the thrust T. Okay, turbojet thrust available. Once again, so this is the thrust available is a sea level thrust multiplied by the density of air divided by density of sea level. So obviously the maximum thrust is available at the sea level, okay? So if you turn on the afterburner, you're going to modify the thrust available using this alternative equation based on the Mach number here, okay? Now obviously this is going to increase the fuel consumption. Okay, so afterburner comes with increased amount of TSFC, typically 50% increase of thrust in full throttle by 200% increase of fuel flow. Of course, it depends on different type of engines. So when you pick up a turbojet turbofan, integrate within your design process, you need to come up with a catalog spec at least. Okay, then catalog spec usually gives you the sea level value you're going to modify with the density of air. Okay. Next one, turbofan and turboprop. Obviously, you have a bypass. Bypass fan. Bypass ratio comes into play also. And also, if you attach this is the high bypass turbofan. This is low bypass turbofan. Turbofan engines. Okay. So the main concern of turbofan is to reduce the TSFC. Of course, you're going to minimize the fuel consumption compared against turbojet. Okay. So bypass ratio comes into play. And then this is the thrust available equation for turbofan type of engine, okay? And then, of course, you can combine turbojet / turbofan with the supersonic variable engine index. You're going to design high-speed airplane to avoid shock wave created from the inlet rip of an engine inlet hitting the compressor blade, which is going to induce the stall of engine. So oftentimes the design of variable engine inlet is required, okay? I don't know, did I have such a thing? Let me just find out. I all of a sudden remember, okay, wait a minute, I had a picture. Maybe I forgot today, I'm sorry. Did I have an engine? Probably I forgot. Did I have a handout? Nope, I don't. Because I still remember last semester I showed something. Let me Google. F14 variable engine inlet or something like that. Let's find out if I can find something. Oh yeah, this is something I showed. Okay, so variable engine inlet, here we go. Yeah, that's it there. So this is F14 variable engine inlet. So depending on the speed regime, in other words, subsonic, transonic, to supersonic, it is going to change the inlet depth. Trying to create the series of weaker shock waves as the flow goes through those weaker shock waves, it is going to minimize the pressure loss as it hits the inlet of a compressor. Okay, so this is fairly complicated, design, and of course you have to simulate over the range of Reynolds number and the Mach number too. What kind of shock wave is going to start form, and then you're going to avoid the strong shock wave forming up in front of a compressor inlet. Okay, so this is one of the subject we covered in last class. It's engine airframe integration type of thing. Okay. By the way, this itself is a good semester-long project. It's so complicated. Okay. Let's just go back. So this is a summary of the thrust model. So you have a variety of type of engines. You can choose piston engine, propeller, turboprop, high bypass, low bypass ratio, turbofan. So those are the equations available for the different type of engines. I guess most of you probably choose the piston engine, propeller type of combination. So you're going to come up with the propeller efficiency and also shaft horsepower. Those are the minimum required catalog spec you have to find. Suppose if you want to design smaller, like a radio control type of airplane, you actually have a real thing, right? Do you have a data for that? Okay, that's good. So you're going to use those kind of things nicely integrated within xFlyer 5. It is going to give you the final distribution of the weight and the center of gravity and the neutral point. Those kind of information you can squeeze out from the software. Okay. So this is, this is the turboprop. So turboprop is going to replace the fan with the prop. So propeller efficiency, of course, comes into play. Okay. This is a ramjet. You're probably not going to use this. This is a high-speed only type of airplane. Usually by itself, it doesn't even fly airplane. Rockets, of course, this is a constant thrust throughout. You just, once you start burning, it just cannot stop type of thing. Okay. Rockets. Okay, so those are the TSFC, okay, for different types of engines. Like I said, this is the temperature, okay. So TSFC changed from sea level to the given altitude. So in order to predict the TSFC for higher altitude, you're going to come up with the either ratio of temperature between the altitude temperature to the sea level temperature or speed of sound ratio. In other words, in terms of fuel consumption, you want to fly higher altitude. That's what your airplane really is. You don't want to stay flying at the sea level. That's where the TSFC is maximum. You want to save your fuel, fly higher altitude. That's what it is. And then oftentimes, if you want to install your propulsion, you are going to have an installation loss of the thrust. So if you get the catalog spec of the engine, it's usually be uninstalled thrust catalog based. So if you try to pick up that catalog based model and then integrate within the real airplane, you oftentimes lose certain percentage of thrust. Okay, so you have to kind of compute those things and integrate within your design. Okay, usually cooling, momentum of cooling of air and power and compressed air bleed requirements, other things, is going to take away certain portion of the thrust, which is on the catalog. But once you integrate, oh my goodness, this is not enough kind of thing. Well, I ended up needing 2 engines. Too bad. That is going to a major modification of your design. But software can do that. Okay. So that's one of the beauties of the using software. If this is a hand calculation, everything is drafted, everybody go insane. I have to draft it again. Now you're using software, so, okay? All right, let's just take a look at example C11, okay? Okay. Where is it? Okay, let's just take a look at the example C11. All right. A new afterburning low bypass ratio turbofan engine produces 15,000 pounds of thrust in military power. What is military power, by the way? No afterburner. It's dry. Okay, dry / wet is like military power or with afterburner. So there are terminology only Air Force Academy people understand. So let's just get used to it. So this is no afterburner, A/B. Okay, 22,000 pounds of thrust in afterburner installed in static seat-level atmospheric conditions. Okay, so 15,000 pounds without afterburner, 22,000 pounds of thrust in afterburner. Installed, static seat-level atmospheric condition. Its TSFC for these conditions is 0.8 per hour in military power and 2.2 per hour in afterburner. What are its military and afterburner thrust as well as TSFC at H equal to 20,000 feet and Mach number equal to 0.8. So this is very simply, you're going to actually estimate based on the sea level catalog spec, you're going to estimate actual value of thrust available at the given altitude. Okay, so let's begin with for altitude, 20,000 feet, okay? You're going to pick up the standard value of atmospheric condition. Density will be at the 20,000 feet. If it's a standard day, this is going to be 0.001267 slugs per cubic foot, okay? And then based on the temperature at the 20,000 feet, you're going to compute the speed of sound, which is the square root gamma t. So if you plug in gamma and R and T as temperature, this is going to be 1,036.9 feet per second. So this is the speed of sound at the standard 20,000 feet altitude. Okay. So first of all, military power, no afterburner. This means you don't use afterburner. Okay. Thrust available is thrust at the sea level multiplied by the density ratio, density over density sea level. So thrust at the sea level is given catalog spec 15,000 pounds. Let's multiply by the density ratio. Density given at the 20,000 feet is 0.001267 slag per cubic foot. Now you're going to divide by standard sea level density 0.002377 slag cubic foot. Okay? So this is going to give you thrust available at the 20,000 feet, military power only 7,995 pounds. In military power, no afterburner. So at the 20,000 feet altitude, this is the thrust available for this propulsion system. Okay? This is the low bypass ratio turbofan. So this is TA, thrust available at 20,000 feet. Okay. So the next question is, what is the military power TSFC? Okay. So let's use the CT. This is the TSFC, okay? So TSFC is a CT at the sea level. Again, the ratio of the speed of sound or ratio of the temperature, either way. Actually, wait a minute. Wait a minute. Is this a correct equation? Yeah, it's correct equation. Let's be careful. If you use the temperature ratio, square root needs to come in because A equal to square root gamma T. That's why. Okay, don't forget the square root if you use the temperature ratio. If you're using speed of sound ratio, it's just a ratio. Okay, good. So this is the correct equation. All right. So given sea level TSFC value is 0.8 per hour. Let's multiply by the ratio of the speed of sound. 20,000 feet is 1,036.9 feet per second. And then sea level value is 1116.2 feet per second. Once again, square root gamma RT. Temperature is the standard sea level temperature. Okay? So this is going to give you TSFC 0.74 per hour. In military power at the 20,000 feet. So this is the TSFC at 20,000 feet. Okay, so obviously, if you compare against sea level value, TSFC is much better because you're going to consume less fuel at the higher altitude, but you're going to lose your thrust. That's what it is. Next, okay. Next is with afterburner, okay? With afterburner, okay. So first of all, you're going to pick up the similar equation. Thrust available is equal to thrust at the sea level multiplied by the density ratio, rho over rho sea level, multiplied by 1 plus 0.7 Mach number of a free stream. So you're going to plug in 22,000 feet, sorry about that, let me just erase it. So sea level afterburner thrust is given, which is 22,000 pounds. With afterburner on at the sea level, you are going to expect 22,000 pounds thrust at the sea level. Then you're going to plug in, once again, density ratio, which is 0.001267 slag cubic foot divided by 0.002377 slag cubic foot multiplied by 1 plus 0.7 times Mach number 0.8. Okay? This is going to give you, with afterburner on, you're going to expect only 18,293 pounds at the 20,000 feet. This is going to be a thruster variable with afterburner on at 20,000 feet altitude. Okay? And then similarly, you can compute the TSFC, which is CT. CT is actually meaning TSFC. Is going to be similarly CT at sea level multiplied by the ratio of the speed of sound. So this is going to be 2.2 per an hour. This is the TSFC at the sea level with afterburner on, multiplied by the speed of sound ratio, 1036.9 feet per second, divided by 1116.2 feet per second. This is going to be decreased to 2.04 per hour. This is the TSFC at altitude 20,000 feet. So this is actually a very simple process. You can predict loss of thrust. You know, the thrust is going to be decreased as you go for high altitude, and also at the same time, TSFC is going to improve for high altitude. So you can compute those things. Okay. All right. So it's 1 o'clock, and then because of the very low motivation level, I can sense in the classroom. So let's just stop here. So next class after your exam, let's pick up SLUF, straight level unaccelerated flight, SLUF condition. So we are going to pick up lots of things out of this plot. This is called the thrust required, thrust available plot. Okay, so we are going to start from straight level unaccelerated flight, SLUF condition. We are going to predict the range and endurance and sink rate and climb rate, other things. So let's just stop here at page 10, and then I'm going to release you early to study for Thursday's exam. So if you have any question, please just send me a Microsoft Teams text chat. If I can respond, I try to instantly respond. For some reason, I just suppressed Jimmy's notification was suppressed. I don't know. I didn't do it. So I just kept missing his incoming request, but I was wondering, oh, wait a minute, notifications off for Jimmy. I don't know why. It's not intentional. I mean, I swear. But anyways, have a wonderful day. We're going to see you back here on Thursday, everybody in class, because it's an exam. Exam cannot be done online. So please show up. Okay. Have a good day. Do you have any question, people online? Doing okay? Okay.
Are you at it today?
No, I had last week talking about writing.
No, what did she, or who you have? I'm sorry. I have Dr. Sula. Do you have the paper that says what we're supposed to write out? We didn't get that yet. She said she posted it on Canvas.
Okay, I'm going to stop recording.